Okay, on example 6, I'm going to show you a technique that can be used on more complicated limits later on. Right now, you might be thinking, "Why are we doing this?" Because we already know how to answer these. Let me just show you. Um, Leading coefficient. These two degrees are the same, so this should be two, right? And it is. But let me go ahead and show you the technique. And the technique is to divide by the highest power of the denominator, divide every single term by that. Okay. And so what you would have then, if you did that, is the limit. And you're like, why would you do this? Well, there are some times where they're a little tricky, and doing this technique would help you on some more complicated things. And you'll see. All right. So if I divide everything by x squared, all right. So I'm dividing every single term by x squared. I don't know how much to show. I'll show everything. All right. So 2x squared divided by x squared. Okay, minus 10x divided by x squared. And then on the bottom, x squared divided by x squared minus 8x over x squared. And again, I know you're thinking, we already have the answer. Why are we doing this? All right, well, you'll see. Okay, so then, so that would equal then the limit as x approaches infinity of, oh, sorry. Okay, so that's 2. All right, minus this weird 10 over x squared thing. All right, and on the bottom 1, and then this would be what, 8 over x, and then this 15 over x squared. Yeah. And then you just apply the limit to each of them. And so this would approach all these ones that have x's on the bottom, or x squared makes no difference. They're all equal to 0. And so end up with 2 over 1, 0, those three are 0. And I'll just show it. And there we go. It's 2. Okay. So once again, you're like, I already knew that, but you'll see this will come in handy. Okay. So same, likewise on this one, let's divide everything by x squared. Oh, by the way, it's bigger on the bottom. It's bottom heavy is what Gene said. So that one is 0. But if we do the technique again, we've got the limit as x approaches infinity, and I see the graph over there too, kind of showing what we're talking about. So I've got x divided by x squared plus 3 divided by x squared. All right, divided by x squared divided by x squared. 4x over x squared. And 5 over x squared. Yeah, it kind of hurts me a little bit to do this, but it's going to pay off later on ones that are tricky. I know I've said that already, but. Okay, so here we have, it's like 1 over x. And then that one doesn't change, 3 over x squared. And this is what allows us to have an answer, because on the bottom, we've got a 1. All right, that's going to allow us to have an answer. And then what do we got? A 4 over x. And then a 5 over x squared. Okay. And so once again, on top, I've got a 0 and a 0, because those have x's on the bottom and on top. And so those will, as x gets very large, those all will approach 0. And on the bottom, we have that 1, which saves us, allows us to have an answer, because we will not have a 0 in the denominator. Boom, answer is 0. Okay, and then likewise here. Okay, if I divide by the highest power in the denominator, highest degree term in the denominator, I'm going to divide everything by x. Okay, and just see what happens on this one. But you can see from the graph over here, this thing's growing without bound, but we will talk about this line that's approaching in just a second. Okay, so here we go. This time I'm just going to show the result. I'm dividing everything by x. Everything by x. So if I divide this by x, we have x. Divide that by x, you got 4. Divide this by x, you have 3 over x. Okay, and then divide this by x, you get 1. And divide that by x, and you get 2 over x. All right. And so what's happening then is as x gets approaches infinity, this thing is still here. Sure, that's a 0, that's a 0, that's a 4, that's a 1, but this is infinity. So it's infinity minus very small amounts, minus 4, minus this, it's going to infinity. And you can see on the graph. But let's talk for 1 second about this line that's approaching. This is a slant asymptote, oblique asymptote, sometimes it's called, but slant is what I mostly heard it. So if we did a little synthetic division right here, we can actually divide this and rewrite this. So, so a little synthetic division. My coefficients are 1, -4, and 3. Okay, and all we're doing is rewriting it. So 1, and then you multiply and you add, if you recall doing that. We don't have a whole lot of that happening in calculus, but it is happening here. Okay, so yeah, and so that's a -4, which gives me a -1, and I think I saw something different on her key. So 1, -4, oh, here it is, I messed up, -3. All right, so that's -7. Okay. There we go. Okay, now remember that's a remainder. So that means this then, all right, check this out. This is the limit as x approaches infinity of this, which is x minus 2 minus 7 over x minus 2. All right, if you recall doing that. Okay, so what I'm saying is, as you approach infinity on this part right here, the remainder part is going to go to 0 because again, it's bigger on the bottom. Okay, so this thing is going to approach. It's almost as if I can say that it's going to approach a line x minus 2. That's what this line is. This line that they have graphed here has a y-intercept of -2 and a slope of 1. Boom, 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 all the way up. All right, and your scale is weird. That's why it doesn't look like it's got a slope of 1. But that's it. So that's kind of odd to say all of that, but that's exactly what we've got, because still going to infinity though. So I think I don't like that I wrote this. Yeah, that limit would still be infinity because x is infinity. Okay, or approaching infinity. So really just right here, just this note here, that forget the limit notation for a second, that as x gets very, very large, it's as if this curve is this. So there's still the limit idea is happening. It's just that fraction went to 0 as x is getting very, very big. But I didn't want to write that as the limit. Maybe if I continued and wrote the limit right there also, that would be proper. Yeah, probably so. But anyway, the idea here is that you're approaching this line as x gets very, very large. Okay, never is the line because we still have that little remainder part, but it approaches it.